Tricks are really helpful sometimes. So this is the typical example of where trigonometric substitution can make a big difference. So let's see how. We have the integral from 0 to infinity dx over x plus square root of 1 plus x square whole to the power n, where n is a positive integer greater than 1, right? So let's see how we can deal with this. Integral from 0 to infinity dx over x plus square root of 1 plus x square to the power n. Now a suitable trig substitution that occurs to me is substituting x as tan theta, because we know that 1 plus tan square theta is just sec square theta, right? Yeah, so because this property holds true, we see that this will reduce to simpler fraction, right? So if I make the substitution, we know that dx will be sec square theta d theta, and the limits will also change. So basically for x is equals to 0, tan inverse 0 is 0. For infinity, tan inverse infinity is pi by 2. Dx is sec square theta d theta. In denominator, we will basically have tan theta plus, now this is square root of sec square is just sec theta to the power n. Now how do we simplify this further? For that, try to notice this fact that sec square theta minus tan square theta is actually 1, right? So if you notice that, I can write this as integral from 0 to pi by 2 sec theta minus tan theta to the power n sec square theta d theta. And the reason is what I have done is basically I just introduced 1 to the power n over here, right? And then I wrote 1 as this factorized form, and then I did the division. So that makes sense, right? Now up to this point it was pretty simple, right? Now what to do? Because there's this pretty complex expression, right? If you want to single each of them out, you can maybe use the binomial expansion, but that will again be pretty complicated. So what do you think of doing? So in this case, maybe try the integration by parts, right? Who knows, it can be helpful. Yeah, so let's try integration by parts, because this is integrable. So yeah, let's see, make this as u and this as v. Okay, so I is equals to u will be as it is, there will be no operation on u initially, and the integral will be tan theta minus integral from 0 to pi by 2. Now its derivative will be n sec theta minus tan theta to the power n minus 1, and now the derivative of individual components will be sec theta tan theta minus sec square theta, right? And the integral of sec square is tan theta d theta. This seems pretty complex, but I hope it's not. I is equals to, because most of the time in maths, easy things might have a big number of manipulations, but those manipulations are usually easy. Over here, notice that I will write plus over here, because I basically want to take minus sec theta common from here. Let me show you the region. Okay, from here I will basically take minus sec theta common, so that we will have sec theta minus tan theta, which I can multiply over here. Yeah, so what I will get now is this will be plus integral from 0 to pi by 2 and sec theta tan theta. What happened is the minus of sec theta went out and minus minus became plus, right? And over here there's sec theta minus tan theta, which when multiplied gives sec theta minus tan theta to the power n d theta, right? Now also I can take this n outside of the integral, because usually constant should be outside the integral, right? Again we have another integral. Again we can do integration by parts, because sec theta minus tan theta, this is easily integrable. Let's try that. Yeah, so we will have I is equals to sec theta minus tan theta to the power n tan theta plus n times integral from 0 to pi by 2. Now this thing, and I forgot to, okay. Yeah, I think you understand this just from this common sense, yeah. The limits of the integral, which it can be understood even though I haven't written it, yeah. Over here also, if I use integration by parts, I think this will basically be removed, right? And so we will have sec theta minus tan theta to the power n times sec theta, and then minus again n times, this will be n sec theta minus tan theta to the power n minus 1. Derivative will be sec theta tan theta minus sec square theta, and integral of sec tan will be sec theta d theta. I hope this is making sense. Please don't get lost in the middle. So this is tan theta, right? And sec theta minus tan theta to the power n. This is from 0 to pi by 2, of course. And again, there is this plus n sec theta minus tan theta to the power n. This is also from 0 to pi by 2. And minus n square integral from 0 to pi by 2. Over here also, if I take minus sec theta common, I can make this plus and write sec square theta and sec theta minus tan theta, right, to the power n d theta. Now there is something interesting over here. The interesting thing is, this is our original integral that we started with, right? See over here, this is the original integral. So what I can say is, I can take sec theta minus tan theta to the power n common, yeah, and then write tan theta plus n sec theta plus n square times I, right? Now I can take this to other side, so I times 1 minus n square is equals to sec theta minus tan theta to the power n tan theta plus n sec theta, right? So I is equals to sec theta minus tan theta to the power n tan theta plus n sec theta divided by 1 minus n square, right? Now I will evaluate this integral. This is our basically this is our indefinite integral, and we can also evaluate indefinite integral at last. Yeah, that won't be a problem actually. So yeah, now let's evaluate this from 0 to pi by 2. Now, many of you will notice some problems while evaluating this at pi by 2, right? Because at pi by 2, sec theta also goes to infinity, right? At pi by 2. Also, tan theta goes to infinity, right? At pi by 2. So there's actually infinity minus infinity over here. And that's an indeterminate form, right? And for indeterminate form, we need to take limits. To find the value, for evaluating indeterminants, we need to take limits, right? So at pi by 2, this will be slightly difficult to evaluate, I guess. But yeah, we will do it. So let's see how to evaluate this. Now let me do a separate section. So we basically want to find limit theta goes to pi by 2 of this expression, right? This whole expression. And also there's this other expression. This also goes to infinity, and this also goes to infinity, right? Now, how we can simplify this is, I'll try to write it as tan theta plus n sec theta divided by sec theta plus tan theta to the power n. I can do this, right? This is the same word technique that we used at the beginning. Now notice that these two expressions go to infinity, right? And they are also raised to power of n. So this is basically infinity also raised to power of n. In numerator, yeah, both of them are going to infinity, but that is just linear combination with n. So this is just the linear combination of infinity, but this is the nth degree combination of infinity. So of course this should be way bigger than numerator. So this should go to 0. So that's a logical intuition, but maths is not based on intuition. We need to prove it, right? So to prove it, what we can do is we can use squeeze theorem, right? We can use squeeze theorem. So what I can say from squeeze theorem is this: limit theta tends to pi by 2 of tan theta plus n sec theta divided by sec theta plus tan theta to the power n. This will be less than or equals to limit theta tends to pi by 2 of, because n is greater than 1, right? Since n is greater than 1, so okay, wait, the space is not enough. Let me rewrite it because this space is not enough. Okay, so limit theta tends to pi by 2 of tan theta plus n sec theta by sec theta plus tan theta to the power n. This will be less than or equals to limit theta tends to pi by 2 of n tan theta plus n sec theta by sec theta plus tan theta to the power n, right? This is because n is greater than 1, and also this will be less than or equal to limit theta tends to pi by 2 of tan theta plus sec theta divided by sec theta plus tan theta to the power n, right? Now let's say this limit is L. Now this will be less than or equals to, over here I can take n common and then cancel it to the denominator, right? So that will be n by sec theta plus tan theta to the power n minus 1. This greater than equals to limit theta tends to pi by 2 of 1 by sec theta plus tan theta to the power n minus 1. Now infinity minus infinity is indeterminate, but infinity plus infinity is infinity, right? So if you use that, this will just be n over infinity, and since n is an integer greater than 1, n over infinity, yeah, this denominator is just infinity right now, because infinity plus infinity is infinity, and then infinity to the power n minus 1 is infinity, so n by infinity is basically 0. Over here this is also 0, so therefore by squeeze theorem I can say that limit is equal to 0. So for our original expression, if we evaluate this is pi by 2, this will be 0, right? Now let's get back to our problem. Okay, so we were evaluating that, right? We don't have enough space, I guess. So maybe I'll just manage, or shall I write it again? You can skip this part if you are feeling that your time's being wasted, but let me write again. I is equals to sec theta minus tan theta to the power n by tan theta plus n sec theta divided by 1 minus n square from 0 to pi by 2. We just found out that at pi by 2 it's 0 minus, now it's 0. Sec 0 is just 1 minus tan 0 is 0 to the power n. Tan 0 is 0 plus n times sec 0 is 1 divided by 1 minus n square. So this is now n by n square minus 1. So this is the required answer of our original integral, right? So the answer is n by n square minus 1. The answer is pretty simple, and the answer looks pretty nice, but the solution wasn't really that nice, I guess, because we had to do a lot of integration by parts as well as a really good limit. Yeah, so that was it. Hope you enjoyed the video. Thanks for watching. And yeah, I have already checked this answer from Wolfram Alpha calculator, so you can be sure that it's the answer. Thanks for watching, and look forward to seeing you in the upcoming video.